Today's webinar, my name, by the way, is Rick Frage. I am the sales director of SFTec. Today's webinar presented by Dr. Girish is about seismic behavior of concrete elements reinforced with GFRP. So about Dr. Girish, he received his PhD in civil engineering from the University of Sherbrooke in Quebec, Canada. And before that, he did a master's of technology in earthquake engineering from India Institute of Technology. So basically, he's the right person to speak to you about seismic behavior of any element, specializing in GFRP anyway. He received also a gold medal in 2013 for Bachelor of Technology project on strengthening of reinforced concrete columns with externally bonded fiber reinforced polymer from the Veer Swendra Sai University of Technology in India. His research interests include the behavior of structural concrete reinforced with fiber reinforced polymer, testing and characterization of FRP behavior, nonlinear finite elements analysis of reinforced concrete structures. So Dr. Girish is a senior structural engineer at SFTec. We are based in Montreal, Quebec in Canada, and a MyTax postdoctoral fellow at the University of Sherbrooke. He has assisted us in many projects, whether designing from scratch or converting a project already designed with steel and converting it to FRP. He worked with us on structural slabs, footings, columns, you name it, bases for communication towers and so on. So he has a very diverse experience in very different zones in North America as SFTec works across the continent. So the mic is yours, Dr. Girish. Please go ahead.
Thank you, Rick, for the brief introduction. Now moving with our presentation today. Today's topic is the seismic behavior of concrete elements reinforced with glass fiber reinforced polymer bars. So during the presentation, I will start with a brief overview of the basics of the earthquake, how it occurs and it impacts, the design code recommendations for the concrete elements reinforced with fiber reinforced polymer bars, and the various ongoing research on the concrete elements reinforced with FRP bars, and we'll conclude the presentation after that. So before starting the main presentation, I would like to give a brief overview of SFTec. So generally our products are mostly designed in Canada and are manufactured in China by Shandong Safety Industries Co. Limited, who are specialized in manufacturing of fiber reinforced polymer products. So we work with national and international engineering firms. We work with them through the design process and help them with the fiber reinforced polymer design standards, whether they are in Canada or in the United States. We focus on the parking facilities, water treatment plants, and retaining walls. And our main focus is only on the glass fiber reinforced polymer bars and the carbon strap applications. So the fiber reinforced polymer bar is made from composite materials. The composite materials can be fiberglass, carbon, emerald, or basalt. And it is manufactured by a pultrusion process using a mix of recycled fibers and resins. So this figure here shows a microscopic view of the fiber reinforced polymer bar. You can see the resin and the fibers. So there are generally nowadays 4 different types of fiber reinforced polymer bar. And in this figure, we have shown only the 3 different types: carbon, aramide, and the glass. And the stress strain plot shows how these fiber reinforced polymer bars are compared with the steel bar. So 2 points should be noted from this plot. First, the glass fiber reinforced polymer bar have low strength compared to the other 2 fiber reinforced polymer bars. And the second, the strength of all fiber reinforced polymer bars are higher than the steel bar. But however, their behavior is linear elastic up to the failure. So we can produce different types of fiber reinforced polymer products depending on the project requirement. And some of the FRP bars we produce are straight bar, spiral, stirrups for transverse reinforcement, bent bars, and glass fiber reinforced polymer shear connectors. So the glass fiber reinforced polymer bars is widely used due to its production cost and have better tensile strength compared to the other fiber reinforced polymer bars. Some of the advantages of the SFTec glass fiber reinforced polymer bars over the conventional steel bar are it have a longer service life because of its corrosion resistance. So therefore, improved durability in harsh environments such as construction near coastal areas and in North American cold climate. The FRP bar have better resistance against corrosion compared to steel bar. And as I told earlier, the tensile strength of the fiber reinforced polymer bar are 2 to 3 times more than that of the steel bar. However, it have more tensile strength. Fiber reinforced polymer bar are lighter due to low density compared to the steel bar. And due to the corrosion resistance, fiber reinforced polymer bar are good for harsh chemical environment as well. And it is neutral to electrical and magnetic disturbance, useful for applications such as airport, military application, MRI rooms, and in hospitals. So some of the selected field application of SFTec fiber reinforced polymer bar, which we have already done in Canada. The GFRP reinforced concrete waffle flooring slab designed with aseptic glass fiber reinforced polymer bar, which was built in Halifax, Nova Scotia. And it can also be used for slab on grades. It is a non-structural slab and it is a one-to-one replacement and saved a lot of money compared to the steel bar in terms of labor and transportation. So another project shows the cast on site, recast sandwich panel, and they have used the SFTec glass fiber reinforced polymer bar in their project as reinforcement, and it was built in China. And in the right is a retaining wall built for the city of Montreal. The retaining wall is designed to dump snow with de-icing salts during the winter. So they built this retaining wall with the glass fiber reinforced polymer bar, which provided resistance against the chemical used in the de-icing salts. Now, coming to the main presentation. So the reinforced concrete columns have many practical applications. So they are used in commercial buildings, emergency buildings such as hospitals, bridge piers in highway, railway and metro bridges and flyovers. And with the increase in the sale of the car year by year, we will need more parking facilities and the recreational area. And those parking facilities will be the multi-story parking facilities, which is built on concrete, reinforced concrete structures. And the practical application of concrete walls can be found in commercial buildings, high-rise buildings, bridge pier and abutment, and nuclear facilities and underground parking garages. And as we all know that there has been a problem of corrosion with the traditional steel bar in reinforced concrete structure. And what is this? The expansion of the steel due to the resulting rust creates tensile stresses in concrete, which lead to cracking, delamination, and spalling, and finally leads to partial or full collapse. And in addition, the seismic design and evacuation of corroded section have lower ductility, which means their plastic deformation is limited. And thus, let's come to the basics of the earthquake. So if you see in the figure, the water molecules at the bottom of the kettle gain heat energy from the flame and vibrate faster and move further apart, and their density decreases. And the hotter particles rises to the top of the kettle, and the colder, less dense molecules move into to replace the hotter particles. And this whole process is called the convective flow of water. So similar kind of process can be found observed in the earth mantle. The earth is divided into the inner and outer core, the mantle and the crust. And the crust is further divided into plates, which is called tectonic plates. And the conventional current in the mantle causes the plates to move in different directions. So after moving in the different direction, they form a large number of tectonic plates. And you can see here a lithosphere. In the lithosphere, it is comprises of a large tectonic plates which has been moving slowly. And there are total 14 number of tectonic plates. And you can see through North America near the British Columbia and California, there is one tectonic plates moving. And let's see how it's moved. So as the tectonic plates are slowly moving, so their edges are locked in place, and this causes the bending of the crust along the plate's edges, so which create a fault zone. So there are two main classification of faults: deep slip faults and strike slip fault. And the figure here is showing the strike slip fault in the San Andreas, California, which is visible to the naked eyes. So if you want to learn more about the earthquake, you can go to this link and you can learn about the faults, earthquake waves, which can be found at this link. Now, the failure due to an earthquake are devastating and can cause shear and compression failure, as shown in this figure. And the fiber reinforced polymer can be helpful in controlling the damage during an earthquake, which will be discussed later in the presentation. So why we should select fiber reinforced polymer bars? So because of the following characteristics, the fiber reinforced polymer bar have resistance against moisture, alkali effect, chemical attack, which mostly depend on the selection of appropriate resin, manufacturing process, and application of protective coating. So therefore, the glass fiber reinforced polymer bars have resistance against deterioration due to chloride ions and carbonation. The second point is the fiber reinforced polymer bars are lightweight, non-conductive, and magnetic free. The properties of the glass fiber reinforced polymer bar available at SFTec are the following. The bar diameter generally varies from the 6 mm to 35 mm, which have a nominal cross-sectional area of 32 to 1006 mm square. The tensile strengths depend on the bar type, whether it is classified as bar 1, 2, or 3, based on the CSA S806 code. And the lower value of the tensile strength correspond to the lower value of the tensile modulus or elastic modulus, which is 46 gigapascal. So the Canadian design code CSA S806 provides guidelines for the seismic design of fiber reinforced polymer reinforced concrete members in new construction, which is given in the chapter 12 of the CSA S806. And the structural element of the moment resisting frame can be either reinforced with longitudinal steel bar and transverse fiber reinforced polymer bar, or it can be reinforced with fiber reinforced polymer bar in both directions, both longitudinal and transverse direction. So the members of the moment resisting frames are generally beams and columns, and the special detailings required for this member will be discussed in the following section, starting with the beams. So the beams should conform to the longitudinal requirement of the CSA 823.3 in case of the longitudinal steel bar, and the requirement of the CSA S806 should be followed if you are using the glass fiber reinforced polymer bar as longitudinal reinforcement. So the beam of moment resisting frame should be reinforced with transverse fiber reinforced polymer hoops or grids in accordance with the chapter 7 in the CSA S806 code. And the transverse fiber reinforced polymer hoops or grids should be placed over a length equal to 2 times D, where D is the effective depth of the beam measured from the face of the connection, and over regions where the plastic hinges are or most damage in the case of the fiber reinforced polymer bar beam could occur, and should be reinforced for a distance equal to the beam effective depth on either side of this this hinge region. The first fiber reinforced polymer hoop should be located not more than 50 millimeter from the face of a supporting member. The maximum spacing of the hoop should be minimum of 1/4 of effective depth, 8 times the diameter of the smallest longitudinal bar, 24 times the cross-sectional dimension of fiber reinforced polymer hoop, and 300 millimeter. And further, the shear resistance of the beam should comply with the chapter 8 of the CSA S806. As you can see in this figure, here generally the hinge will form at the end and support end. So here you can see there is a special detailing is provided for the with the FRP hoop. So the column member of the moment resisting frame should satisfy the relevant seismic provisions of the CSA A23.3 with longitudinal steel reinforcement, and the transverse fiber reinforced polymer reinforcement should be provided in forms of either circular spirals, hoops, rectilinear hoops, overlapping hoops, grids, or cross tie, which is shown in the figure below. The required area of the transverse FRP reinforcement should be calculated using the equation as shown here. And here the P by P naught is the axial load ratio, and which should be greater than or equal to 0.2, and AG by AC minus 1 should be greater than equal to 0.3. And the delta you can see here is the design lateral drift ratio, which is generally 4% for the ductility, for the moderate ductility requirement. And KC is the confinement coefficient, efficient coefficient, which is generally taken as 1 for circular spiral or circular hoops. So the transverse FRP reinforcement should be spaced at distance not exceeding the minimum of 1/4 of minimum member dimensions, 150 millimeter, and or 6 times the diameter of the smallest longitudinal bar. The spatial moment resisting frame detailing of the transverse fiber reinforced polymer reinforcement should be provided in the plastic or most damaged region. So you can see here at the top, at the bottom, where the generally columns are connected, there you can find the most damaged region. That's why this spatial detailing should be provided at the ends. So in the present presentation, the concrete members reinforced with fiber reinforced polymer bars are divided into 3 sections: walls, columns, and moment frames. So which I will discuss one by one. So first, starting with the concrete walls. So the experimental testing of the lateral resisting structural member conducted in 2014 with full-scale glass fiber reinforced polymer reinforced concrete shear walls, and all the glass fiber reinforced polymer reinforced shear wall achieved flexural strengthening with no sign of premature shear, sliding bond, or anchorage failure, and they attended a drift ratio of over 3%. So the advantage of the GFRP reinforcement was no permanent deformation at up to 80% of the ultimate capacity of the shear wall. And the further testing of the 6 full-scale shear walls with different boundary elements, it was observed that the more confinement in the boundary element of the wall enhanced the drift capacity of the wall. As you can see here, there was confinement was double here in these 3 shear walls, and there is an increase in the drift capacity by 50%. And the crack width of the shear wall with more confined boundary element was decreased by 40%. So here you can see some of the examples of the failure of the squat walls in diagonal shear and sliding during an earthquake. The amount of damage caused by an earthquake can be controlled using glass fiber reinforced polymer reinforcement, and which is discussed in the following slides. So due to the lack of experimental results on hybrid reinforced squat walls, so the hybrid, what does the hybrid means? Hybrid means here both reinforcement, steel and glass fiber reinforced polymer bars, both are used in building the shear wall. The finite element model was built and validated based on the previous results on GFRP reinforced concrete wall. The specimen were representative of bridge pier walls in the strong direction. So the bidiagonal wave reinforcement, as you can see here, the bidiagonal wave reinforcement was glass fiber reinforced polymer bar, and all the main reinforcement, the vertical bars were the steel bars. Only these horizontal bars and the ties for the boundary element were the GFRP bars. So the finite element analysis provided accurate simulation of the experimental response of the tested steel and glass fiber reinforced polymer concrete bridge pier walls. Extending the GFRP bars either arranged diagonally or vertically along the wall height was necessary to ensure their effectiveness in controlling damage. Further, they satisfy the demand of ductile recoverable performance up to maximum drift of 2%, which is recommended by ASCE 41. The residual drift of the wall with vertical or diagonally arranged GFRP bars was low compared to the wall reinforced with the steel bar. So as you can see in this figure, which is the residual drift here, which with shear wall reinforced with the GFRP bars at the diagonal wave was much lower. And you can also see from the hysteresis response at the the residual drift is very low as compared to the specimen reinforced with the steel bar. Now coming to the columns. So reinforced concrete columns were tested to study the confinement effect of glass fiber reinforced polymer spiral and cross tie on concrete columns longitudinally reinforced with the GFRP or steel bar. So the failure mechanism for the first tested GFRP reinforced concrete column, the first crack occurs. After that, more tensile cracks begin to appear on further drift cycles. The concrete cover start to split vertically, and on further increment of the drift, the concrete cover start to fall. The longitudinal reinforcement interlaminar degradation was seen. After that, there was a fracture of the longitudinal GFRP bar in compression. And on increasing the drift, the cross tie rupture, and finally the core concrete began to crush. So the maximum strain attained by all the GFRP spiral and cross tie was lower than the 6,000 microstrain, which was lower than the requirement in CSA S806 design code. The GFRP spiral and cross tie doesn't show any failure for most of the tested column, which shows its effectiveness in confining the concrete column core. Glass fiber reinforced polymer reinforced concrete column could be suitable for medium rise structure to low to moderate seismic zones. The compressive behavior of GFRP bars in GFRP reinforced concrete column doesn't provide the plasticity required for seismic response, and it makes it more likely to fail in a BTL mode. So therefore, concrete columns with hybrid reinforcement consisting of longitudinal steel bar and transverse GFRP spiral cross tie was tested, because in the research, it has been seen that it can provide better resistance against corrosion than a column completely reinforced with the steel bars. So therefore, hybrid reinforced concrete column consisting of longitudinal steel bar and transverse GFRP bar were constructed. The figure shows the casing of the hybrid reinforced concrete column, which longitudinal steel bar and transverse glass fiber reinforced polymer bar. The failure progression of the hybrid reinforced concrete column was rapid compared to the glass fiber reinforced polymer bar, which the occurrence of all the milestone as in the GFRP reinforced concrete columns. Only here we can see the buckling of the steel reinforcement and the fracture of the steel bar, which was different from what we observed in the glass reinforced polymer bar concrete column. The lateral strength in the hybrid reinforced concrete column increases until the severe concrete cover spelling and start to degrade thereafter, which was opposite to what observed in the glass fiber reinforced polymer reinforced column, where the lateral strength increased until the failure of the column. So due to the higher stiffness of the steel bar than the glass fiber reinforced polymer bar, the lateral load was more in the initial drift cycle, but after 1.5% drift ratio, it reversed and the concrete cover deterioration and more lateral loads were absorbed in the glass fiber reinforced polymer concrete column. Finally, the GFRP reinforced concrete column attended more lateral load than the hybrid reinforced concrete column. The strain developed in the longitudinal steel bar, various levels above the column stub interface and below the column stub interface were compared. The strain in the longitudinal steel bar showed a jump in the strain after the yielding of steel bar, and at 2% drip ratio, the strain hardening caused the strain to redistribute. The strain gauges installed at 150 millimeter below the column stub interface recorded strain lower than the yield strain, which showed that the development length of the longitudinal steel bar was adequate. This observed phenomena was similar to the observation in the past research for concrete columns confined with the steel ties. So therefore, the behavior of longitudinal steel bar was unaffected by the types of reinforcement, transverse reinforcement used, either steel or GFRP. So here you can replace the steel transverse reinforcement with the GFRP reinforcement, and the behavior will be almost same, and it will be, the structure will be more corrosion resistance. The glass fiber reinforced polymer spiral and cross tie effectively confined the concrete column after the yielding of longitudinal steel bar. We showed as a non-zero strain at zero drift in both spiral and cross tie, and development of significant strain in the GFRP spiral and cross tie at the steel bar buckling. You can see here the development of a significant amount of strain, and which is in some cases which is higher than 2000 strain, and 2000 strain is the yield strength of steel bar generally. So the confinement effectiveness of the steel ties beyond steel strength of 2000 microstrain was generally found to be insufficient. So whereas the strain developed in GFRP spiral and cross tie went beyond 2000 microstrain and provided effective confinement until the failure of the specimen. So the seismic behavior of concrete moment frame reinforced with glass fiber reinforced polymer bar were studied using the pushover analysis, and the intermediate moment frames were 3 and 5 storage with 2 or 3 bays as shown in this figure were designed using the ACI 440. A computer code using MATLAB was developed for seismic design of moment frames. The developed code in MATLAB has the capability to model materials and geometries in SAP 2000, which then derive forces and design the members. So the result from the study were the moment curvature curves at plastic hinge region for beam sections of the 3-story 2-bay and 5-story 2-bay. A moment frame reinforced with GFRP and steel bars were compared. The GFRP bars reinforced section behaved linearly, however, provided higher moment capacity than the section reinforced with the steel bar. The moment capacity of the beams reinforced with GFRP bars to that of the reinforced with the steel bars were always more than 1, attending a maximum value of 1.5 times what the moment achieved by the steel members. So therefore, the considerable moment capacity of the GFRP reinforced section can be achieved even with low reinforcement ratio for resisting the positive moment. As seen in the pushover curves, the moment frames reinforced with GFRP bars show high load carrying capacity because the GFRP bars poses high tensile strength than the steel bar. However, due to the linear behavior of GFRP bars, moment frame reinforced with GFRP bars behave less ductile in comparison with the moment frame reinforced with steel bar. So as the aspect ratio, which is the ratio of the height of the frame to the width of the frame of moment frame reinforced with GFRP bars decreases, the frame displayed better performance regarding the deformability and base shear capacity. So as you can see here, this is the 5-story and this is the 3-story. So the 3rd story have better, with the GFRP reinforcement, have better deformability as compared with the GFRP reinforced moment frames with 5-story. So the initial stiffness of the pushover curves for the 3 and 5-story GFRP reinforced moment frames were 20%, which we can see here the initial stiffness here. So generally the GFRP initial stiffness was always lower as compared to the steel, and this is because of the stiffness, because the steel have higher elastic modulus as compared to the glass fiber reinforced polymer bar. The hinging pattern of the steel reinforced moment frame, which can be shown here, showed a desired beam sideway mechanism. So in other words, it showed a strong column, weak beam mechanism. Whereas the hinging pattern of the frame reinforced with GFRP bars conform a weak column and strong beam condition, leading to a formation of plastic hinge in the columns of the middle story, as you can see here, which resulted in column sideway mechanism due to the failure of the column in the third story. So the top story beam of the GFRP reinforced moment frame doesn't provide ductile performance due to the linear behavior of the GFRP bars, which changes the failure of the frame from beam to the column sideway mechanism, which is not desirable in a earthquake, during an earthquake. So therefore, GFRP reinforced moment frame need attention to avoid such kind of soft story phenomena, and this can be avoided by providing higher stiffness to the columns in GFRP reinforced moment frame. So if you find those columns where we have a soft story phenomena, there we can use the hybrid reinforcement, where we can use the longitudinal reinforcement as steel and transverse FRP reinforcement. In conclusion, the tested wall, irrespective of their aspect ratio, achieved acceptable level of deformation through a stable response with no sign of premature failure. The strain developed in longitudinal steel bar showed that it was unaffected by the type of transverse reinforcement used, either steel or GFRP. The GFRP cross tie effectively confined the hybrid reinforced section after the yielding of longitudinal steel, and GFRP spiral become more effective in confining the column core after the concrete cover is falling. The linear behavior of GFRP bars with considerable strain capacity put it in a position to be considered mainly in frames demanding linear behavior and frames with low to intermediate story level. As I showed that if the storage is the aspect ratio is low, then the GFRP perform better. So further, the soft story phenomena in GFRP reinforced moment frame can be avoided by providing higher stiffness to the columns or vertical members, which can be achieved by using hybrid reinforcement with steel as vertical members, which was shown in the research on the shear walls and the hybrid reinforced concrete columns. So these are list of the North American design codes and guidelines for the FRP bar in concrete structure. So ACI 440 only recommended the use of GFRP bars in case of B or C seismic design categories. And whereas the CSA S806 and S6, they completely give a complete guidelines for the use of GFRP bars. Either you can use it as a hybrid reinforcement, where you can use the longitudinal reinforcement as steel and transverse reinforcement as FRP. So thank you for your kind attention.
Thank you very much, Dr. Girish, for this presentation. Thank you everybody for attending. I just launched a couple of seconds ago like a small poll or survey. It's about 6 questions only. It takes about 30 seconds. We do appreciate your feedback. It will give us also some insight what future subject you would like to learn a little bit more about. At the same time, Dr. Girish is showing our contact information. So if you have any questions, whether it's technical or sales related, here are our contact information, as you can see on the screen. So please do not hesitate to contact us to have your questions answered. Thank you again for your attendance. We hope to stay in touch and keep an eye on our newsletters for the next webinar. Thank you and have a great day wherever you are in the world.